first feel into how Haskell works, and I think if there is any need, and if you want to know something more, we should do something like practical. So this is going to be like showing some of the features, let's say the most core features, and just so that you can get the feel. I've got the feeling when I learned Haskell is that there is a terrible lack of useful learning material, because it's either it doesn't actually go into the structure of the language, or it tries to be a PhD. There's nothing like in between. So I'll try to kind of make it in between, so it doesn't actually, require you to know the whole, I don't know, language structure, but then at the same time, it actually, you can understand what's going on. So yeah, Haskell is now, I guess, the hipster language that everyone likes. So this presentation will contain quite a fair amount of memes. I just felt it like the perfect way. So yeah, it's. I'll start off with this list. So first of all, it's lazy, which means it will only do a computation when the computation needs to be done. So it has some downsides, which means that lazy computations, they take more memory and just a tiny bit more CPU time. But then the advantage is it doesn't actually have to compute what you don't need. And you can actually tweak this laziness, so you can require a certain part to be strict, which means to just compute the whole thing. So you can actually manage this laziness in a way that you can actually do something with it. All the variables are immutable. It's a functional language. So if you assign something to a variable, so you can see the terminal on the right, right? Guys, can you see the terminal on the right?
Yes.
Okay, cool. Because I'm on Linux, and screen sharing on Hangouts is a very hacky business, so at least for me. So we've just created an X and assigned something to an X. But what we've created now is a second variable called X, which is 5. But X itself cannot ever change its value. And if you did something like this in a function, so two variable declarations, it would actually error out saying, oh no, you cannot actually have two of the same variables in one function. Functions are pure unless specified otherwise, which means that the function cannot have side effects, which means that for almost all functions are kind of like mathematical functions. So for the same input parameters, you get the same output. So this is actually pretty useful, because you can very easily, one of the reasons why it's useful is that you can very easily cache some results. So you've got the guarantee that for the same input parameters, you're going to get the same result. The side effects, which is like writing to a screen, reading something from a socket, or writing to disk, something like that. So those side effects are contained in a special way, which means that the function actually has to specify in its types that it wants to use side effects. You cannot use side effects in any function, which gives you this caching property. That's one thing, and the other is that the code is much clearer because you know that this function is not going to depend on anything apart from its input parameters. The type system is, I think, the first type system I've seen that I feel it actually helps. Like type system in C++, for instance, I hate. And this type system, as I'll try to show, is actually very useful and actually does something that works. And the community, well, I just came from a Haskell conference, essentially. The community is amazing. There's actually a lot of very smart people, and they're all very helpful, and there's a lot that can be learned. I'll try to give you some links to the community. Resources. So let's write something. It will be a program. So let's call it hello.hs. and we create a main symbol, essentially. So everything that is run, the only way to run something in Haskell is to assign it to main. You can, of course, run different functions because you can call them from main, but the only thing that's going to be run in the Haskell program is main. So the function put line is executing a side effect, and the side effect is actually writing to the screen. So let's save that and run. What we're doing now is we're running an interpreter on this file. You can also compile every Haskell program. It will compile to machine code with a runtime. But the way that the interpreter works is actually it compiles the whole thing without any optimizations. The reason why it's important is that the order of declarations doesn't matter. Because it doesn't actually execute them line by line when it interprets them. It actually compiles the whole thing. It just doesn't compile it directly to machine code. So the compiled code behaves exactly the same way as interpreted one. So yeah, that's the hello world. Hello world in Haskell is kind of, I feel that many people feel that it's like, it's usually explained in such a way that it's usually a very hard thing to do, hence, yeah, the meme. So the interpreter that I already run, we can also write something out to the console in here. So we can do put string line, hi, and also run the same way, more or less. So yeah, let's go into types. There is a special command in interpreter, which is what's the name of this character? It's a colon, right? So it's a colon T, and it gives the type of whatever follows it. So say the type of a number. So this says that this number 1 has a type of something that belongs to the type class A. So what it actually means? It means that it doesn't actually know if it's a floating point number or it's an integer. So it is going to restrict what can one be to class, so to a collection of things that behave like numbers. We can define our own things that behaves like numbers, but as far as we know, it doesn't actually know what this thing is. So if we do a type of a string that contains A, or let's say AB, so a type of AB is a list of characters, because a string in Haskell, the most basic string type, is just a list of characters. We can, of course, have chars, so a single type of single character is just a character itself. So say if we had, we can have a plus operator. So what a plus operator does, it's a function that takes 2 parameters. It's a funny way of actually the way that Haskell describes parameters. So it takes 2 parameters and outputs a third thing. They're all the same type, and this type belongs to things that behave like numbers. So say we can add 1, 2, and this is going to be something that behaves like a number. So if we add it, we get 3. We can add 2 floating point numbers, and it will actually coerce things that behaves like numbers to the same type, in this case, the floating point type. So those are the basic types. Let's go into something more fancy. So there is a maybe type, which says essentially that something may be there or it may not be. So there are 2 constructors of this type. So you can say take just 2, which means there is something in this type, and this is 2. It is going to be of a type of maybe that contains something that behaves like a number. And we can have nothing, which says there's nothing there, and it can it's of type maybe that contains anything at all, anything that doesn't have any constraint on itself, because nothing contains nothing, which means it can contain anything. So yeah, let's try to implement exactly that. So we'll declare a module, and we'll make it so we don't actually get the maybe that's already implemented, so that we have what we defined. So we've got this. Actually, if we did it like that, we could still have the code. Oh, no, I know what we need to do. So now if we run that and we try doing just for, it will error out. It will say, oh, there is no instance of the class show. So this means that it doesn't know actually how to show this thing, so it cannot show this to the screen. Writing those show instances is pretty burdensome and it's pretty repeatable. And Haskell can actually write those instances for us. So if we can automatically derive this show instance. So let's run it again. Oh, and we have just for, and nothing still works. And the type of just for, it's maybe from the maybe module, which is our maybe. So we've just essentially rewrote the maybe type. So maybe type is either nothing or just something. The order doesn't matter here. It's just this alternative that's needed here. So this is that. So let's talk about recursion. So we want a function that computes the length of the list, right? So this function is going to have a type of anything. It's a list of anything, and it will return an integer, which will be the length of this list. So length of an empty list is 0, and length of a list that contains something. With this is pattern matching. So this means it's a list which has a first element that is x, and then the rest of this list is x's. Is 1 plus length of the rest of the list, right? So length of an empty list is 0, and length of the list that contains an element and the rest is 1, which is the length of this one element, and the length of the rest. So let's save that and run it. So let's try it. Length of an empty list is 0. Okay, this matched the pattern. So length of a list that contains an element is 1. Length of a list with, say, 5 elements is 5. So it's pretty magical, I think, that we've just only said, like, almost in human language what has to happen, and the compiler itself figured out how to structure it into a program. But that's easy. Let's try to write a quicksort. Quicksort in more imperative languages is pretty annoying to write quite often, but we can be much better in here. So we will sort stuff that belongs to this class of things that we can order. So we want to sort things that we can order, because if we weren't able to order them, we wouldn't be able to actually sort them. So we'll accept a list of things, and we'll output a list of things. So let's think about it. So quicksort of an empty list is an empty list. And quicksort of a list that contains the first element and contains the rest is we first take the elements that are smaller or equal to our element. So this is going to be y such that y's are coming from the rest of the list, and y's are smaller or equal than this first element. Then we add this pivot in the middle, and we then take the rest, which is the elements that are bigger than x. So we have those y's come from the rest of the list, and y's are bigger than x. So this is essentially a definition of quicksort. We didn't actually have to do any boilerplate, but let's see if it actually works. So let's run it. So quicksort of 1. Okay, this doesn't error out. Okay, this still works, but this list is ordered. So let's try some other list. Oh wait, it didn't work. Oh, love those cases. Let's say what's going on. Wait, this should work. Live coding, love that. Oh yes, because what I did here is I took the element smaller and I've appended the element, and then I've appended the elements bigger, but I didn't recurse down. So because we still have to sort those smaller lists and those bigger lists, right? So works. And I find this almost magical. Like, we've just essentially said, oh yeah, in order to sort, take the smaller elements, sort them, take this element and sort the bigger ones, and it works. So yeah, this is pretty awesome. But we can get even more awesome. So let's write a Fibonacci sequence, right? The Fibonacci sequence take an int and outputs an int. And the Fibonacci sequence of 0 is 0. Fibonacci sequence of 1 is 1. Fibonacci sequence of any number is a Fibonacci sequence of the previous number plus Fibonacci sequence of the number before that. So let's check if it works. So Fibonacci sequence of 3 is 2. Of 4, no, wait. Fibonacci sequence of 0 is 1. So Fibonacci sequence of 3 is 3, 5, 8, and so on and so forth. Right? So that's fair enough. This is essentially what I've just shown for quicksort. So it just matches to the fact it calls the previous one, and then when it goes down to 1, it just outputs a number and rolls back the recursion, and same goes for 0. But we can write a fancier quicksort. So this quicksort will, this Fibonacci, this Fibonacci will output a list of integers, which are going to be the next numbers in the Fibonacci sequence. So the first element of the list is going to be 1. Second element of the list is going to be 1 also. And then the rest is going to be those two lists zipped together. So let me just write this, and I'll explain it on the following slide. So what does it actually do? Well, we don't know really, but let's try running that. So we've got our second Fibonacci, and the exclamation mark is used to take an element of index, whatever, from the array on the left. So a Fibonacci of 3. Fibonacci of 3 is 3. Fibonacci of 4 is 5. 5 is 8. 6, and so on and so forth. So this worked, but what did actually happen? So let's assume we know what the Fibonacci sequence is. So it's 1, 1, 2, 3, 5, and so on and so on. Then the tail of that, which is all the elements apart from the first element, is going to be 1, 2, 3, and so on. So without the first element. So if we stack those two together, one over another, then if we add the corresponding numbers, so 1 plus 1 is going to be 2, 1 plus 2 is going to be 3, 2 plus 3, 8, and so on and so forth. But, you know, that's all nice and fine, but how does it actually know? How can we assume that we already know this this sequence if we don't know it? It's actually the thing that we have to compute. And that's the magic of laziness in the language, because it doesn't know this number, so it goes on until it learns what the numbers are, and then it rolls back from those ones to give you the actual element. So the actual list that Fibonacci prime creates is an infinite list. So it will, if we don't take a given index, it will actually like compute forever and give us those really long numbers for the elements of the Fibonacci sequence. So there are two things at play. First is the laziness, and the other thing is the fact that because the language is lazy, we can operate on infinite data structures, because we only have to compute up to the point where we want to know something. We don't care really if we take the 6th element. We don't care what the 7th element is, even though in more traditional languages we would. So yeah, that's probably all mapsy questions. So let's try to actually output something. So we have to assign something to this main symbol, and then do is a special thing, which means we can chain commands together. So let's write a function that's going to output, that's going to say if a given thing is odd or if it's even. So let's just paste it over. So it should ask us for a number, then get this number into this variable, then parse it as an integer, and then if the rest of dividing it by 2 is 0, then we say the number, we convert it to a string, is even, and if it's odd, we say it's odd. So let's try running it. So it says give a number, so let's give 4, and it says 4 is even. So let's run it again, and let's give it, I don't know, 11. 11 is odd. Okay, but that's very explicit. So let's think if we can actually simplify it a bit. Maybe we can create a function that accepts a number, and it says if this number is even or is this number odd. So it's going to be like is odd or is even. It's going to have a type of integer, and it's going to output a Boolean value, so whether it's odd or even. So is even accepts a number, and then if the rest is 0, then it's even, so true, else false. So what can we do? We take this line and we can say if is even read line. So we apply, so we pass to is even the result of parsing line, but we don't actually specify the type because the compiler will take the type from the function definition. And then if it's true, then it's probably even. If it's false, then it's probably odd. So we've just got rid of this nasty type declaration there. So let's try running it. Oh yeah, and it said something was wrong because it actually compiles the things without first running it, because we have num here, but num, there's no num around, there's just n. So let's fix that. And then it still errors out because it doesn't have this number in here because there's no num. So we don't actually have to convert to string now. We can just take this string and output that. So let's give a number for is even, and let's try with some other odd number, so 13 or so. So that's one way to simplify. There's a way to simplify it even more, but I wouldn't actually go into that today because that would require actually knowing what monads are. So there's much more awesome things in Haskell. So it's amazing when it comes to concurrency. It can spawn millions of threads, and it actually works because it doesn't spawn system threads, it spawns some internal thing that behaves like a thread. Because those functions are pure, they don't have side effects, so there is a way to very cheaply run them as if they were in separate threads, which means that if we're writing a web server, we can have the advantages of both worlds. So we can have the advantage of an event loop, like it happens in Node, where we don't actually have to spawn these expensive threads, and we can have the advantage of actually having threads, which is like local state that's not somewhere in the event loop, and so on and so forth. And we can have both of those things, and the runtime is going to support. I've tried today, and my laptop, it can it works very fine with 2 million threads, and it's all fine. We can compose those functions. So the simplest function composition that I've shown is probably with this Fibonacci, but we could here as compute. So we could do it like that, which means apply is even to the result of read. So we could chain those functions together and get really powerful effects out of things that are quite terse and also very easy to read. So just to show you that this actually works. So this still works. So we've applied this even to the result of read. Of course, it's a very simple thing. So this is probably more readable in this particular case, but very powerful effects can be created with very little syntax. All of this behavior, so for instance, this main function, it's actually a special thing. So the type of main is actually an IO monad that returns nothing. So this monad, whatever it is, it gives the IO the ability. It gives main the ability to actually output something to the screen. We cannot do it from normal functions. So this function is even. That's the only thing it can do. So the compiler can optimize it very well, and it can actually also have those small, very lightweight threads. There is also a thing called software transactional memory, in which your memory can behave essentially like a database in a multi-threaded environment. So you can share memory between threads, but at the same time, you can have a guarantee of no deadlocks. which is just amazing. It's just a tiny, for most users, it's just a tiny bit slower than not having those transactions there. But it simplifies concurrent development a lot. And there are also other things like arrows and lenses and so on and so forth, but that's probably more advanced. Like one of the, I would say, disadvantages of a language is that you can define very much your own syntax by yourself, because this equals sign in here, it's not a property of a language. It's a function that's implemented in the main library called Prelude, but it's not a property of a language. So you can define your own operators, which people quite often do. So learning a new library is sometimes learning a new set of operators that are different from anything you know so far. So that's a pretty strong advantage, but also at the times it's a disadvantage of the language. So yeah, when it comes to web dev, there are many very stable and especially very performant servers. It's very common for Haskell servers to be able to sustain thousands of connections with no sweat at all, precisely because of those light threads and this model of computation. And there is also quite a lot of libraries to actually do practical things and not implement them yourself. For instance, there's a native WebSockets support, which is extremely performant, and it's also very easy to use. So let's, as a last thing, I've got a very basic server in here. So this uses a snap server. I won't get into what this first thing is. So we're using the snap server, and our site is going to be like a simple thing. It's going to output a string, and we're then going to serve this function, which is a site function that outputs a string with some default parameters. So now if we run this thing, and we can also compile it, of course, to a native code, and it's going to be extremely fast then. So if we run it, it runs on port 8000, so hey, it works. And it's just a line. So we just define the function that outputs the string. So what I find myself with Haskell is that because of the layers of abstraction and because of the fact that syntactically is quite different from anything, it takes some time to actually understand it. But I think that the payoff is very high, and the ease of doing certain things and the guarantees from the compiler are really great. So at the beginning, it's the problem with Haskell is that, yeah, you write something, you get a result, but you don't quite know why. But then you get the feel for it, and then it's there is a moment when it becomes really, really clear what's going on. So yeah, thank you.
Thanks so much, Michał. It was an awesome presentation. Do you guys have any questions to Michał?
Okay, and if you have any questions about Haskell, if you wanted to, learn it yourself or take a look at some learning material or something like that, I'll be more than happy to provide you with some links to some things that are very useful. Or if you want some help with something that you're trying to write or whatever, then just ping me on Slack and I'll be there to help.
Awesome. Thank you so much once again, Michał. You won yourself a t-shirt. It is still being designed, but it should be ready soon.
Well, I guess I'll get it on Friday then, right?
Well, maybe another one. Thank you so much once again, and thank you guys for attending the course. See you next time.
Yeah, thank you, Michał. Thanks. Bye-bye.
Thank you, guys. Bye.